Welcome to Ushendra's engineering tutorials. It's something about dual input balanced output configuration of a IC741. It's like this. Which arrangement is known as dual input balanced output? Stay with me. I'll tell you what it is. Two transistors connect like this, having a face-to-face two transistors like this with a collector. As we all know, now this will be the emitter and this will be the base. Here with another transistor Q2 we have the emitter over here, and if this is the this is the base and this will be the collector like this, and connected to the supply plus VCC. It's a DC voltage plus VCC. Hope it's clear to you. And here we have a collector load resistance RC, even this is RC, load resistances. Now going ahead, the connection would be both the emitters are commonly connected here, both the emitters are connected, and we have a resistance, external resistance RE over here, RE, and connected to a minus VEE, VCC to the collectors, VEE to the emitters. Right? We are not yet done. So here we have a we need some source, right? Input here. Now we are connecting it's a base. Now this is the base of the transistor B1 and B2 of Q2, and we have resistors, source, input source, sorry, it's not resistor, input source like this. It's a AC source V in 1, and we have another source, it's also AC and designated as V in 2. Okay, now this is, and not yet done. To justify this one, dual input, dual input, two different inputs, balanced output. For this, how we justify for this one, or generally common emitter configuration, the output is collected across collector, right? When the output is collected across here, let it be VC1, voltage across collector, and let this be VC2, voltage across collector 2 of the second transistor. When the output is collected across both the collectors, that output is known as balanced output, right? So in some other case we have unbalanced. Let me tell you when that discussion comes. For the time being, when the output is collected across both the collectors, that output is named as balanced output. And what we have over here is V0 will be equal to, very important equations over here, V0 output voltage, V0 equal to VC1 minus VC2, or else even this is true, VC2 minus VC1, both are true. Analysis leads to the same final equations, right? And in order to evaluate some important derivation, we have to check the flow of current, etc. Here it's a base. You guys, something else to be added over here. It's a source resistance. We have a source, the internal resistance of the source R I1, and even this includes a source resistance R I2. Right, now we have to bother about the currents and voltage drops, etc. Here it's a base, so IB1 will be flowing. It's another base, so we have IB2 flowing over here, right? And the collector here, it's a IC1 over this side, and we have a IC2 over that side. And careful watch, now we need your more attention. It's emitter, right? It's emitter, and this is emitter. Both the emitters are short circuited and then provided with this one. So we'll be having IE1 over this side. It's a IE1, don't get confused, I'm sorry, don't get confused. It's a IE1 over this side, and we have IE2 on this side, and that will be flowing only up to this node. After this node, the current over here, the drop would be like both the currents will be flowing through this one, IE1 plus IE2 will be flowing over here. Please make a note of that one. Be cautious about that one. We cannot overlook that. On the other hand, as far as transistors are concerned, it's a common emitter configuration transistor, and as far as transistors concerned, we have the gain ratio beta. Remember beta, alpha, beta. Here in this case, we need the equation for beta. We need to plug in the expression for beta somewhere for the simplification. And here beta is given as, what is that ratio? Beta, most probably AC. If you're talking about AC analysis, beta AC will be equal to, I guess it's a I E by I B. Please make a note, even this is an important one here, right? Even this is important equation. And on the other hand, generally IC, the collector current IC will be approximately equal to IE. In the sense, IC can be substituted with IE. Please make a note, even this one. These are all important prerequisites to plug in somewhere to reach to final expression, right? And from the dual, now this is one dual input, two inputs, V in 1 and V in 2, dual input, and when the output is collected across both the collectors, we have we call that as a, what is that, a balanced output, right? And it will be asked to evaluate the gain of the amplifier. It's a differential amplifier. Differential amplifier because the output is the difference of the two inputs. Here it's a differential amplifier, being the input of a IC741, and with this arrangement, when two transistors are connected in this manner and with RE, this arrangement provides a very high gain, which is very much required for a IC741. The required very high gain for the IC741 is provided by this arrangement. Single common emitter transistor has a very high gain, and when two transistors are connected in this manner, that provides even more very high gain, and hence the input impedance, the input resistance of a IC741 is very, very, very high, which should be put in inverted commas, please. Why? Because based on this statement, we neglect some parameters and we consider some parameters in the ongoing. A lot of discussions, a lot of derivations to be done based on this one, and this statement will lead to a lot of simplification. What? The input impedance of a IC741 is very, very, very high. It may be in the order of mega ohms, right? Input impedance is very high. Please make a note. The input impedance of a IC741 is very high because of this one. This configuration provides a very high input impedance, right? And the gain should be the voltage gain, input resistance, etc. has to be evaluated of the dual input balanced output configuration. For that, we need the AC equivalent of this one, right? How to obtain the AC equivalent of this one? We have, this is a DC source here, plus VCC, it's a DC, that has to be grounded. Even this minus VE, even this is a DC source, that has to be for a AC equivalent, right? And we have AC input. Transistors are short circuited. This one, transistor is short circuited like this one. Let me redraw it for you. Here, both the emitters are shorted and commonly connected to RE. Let me draw that. Both the emitters are short circuited, and we have RE over here, RE. What current flows through RE? We need that for analysis, okay? So I won't be mentioning over here. I've told you for AC equivalent, this will be the AC equivalent of that one. AC equivalent, all the DCs will be made 0, right? And the transistor will be short circuited. That's the procedure to draw the AC equivalent. And on the other hand, RE, what current flows through RE? It's here, IE1 plus IE2 will be flowing through RE, right? And on the other hand, go ahead like this one, come over here. Here we have done with this one. What is here? On the other hand, we have what? This one, base. We have a base over here, and base connected to what? The source. We have, it's a AC source that cannot be eliminated while in AC equivalent, and this is grounded as usual and given the name V in 1, isn't it? It's a V in 1, and we cannot neglect that internal resistance. It's a RI1, some sort of the notation, that's it. And what current flows through that one? Hey guys, it's IB1 flows over here. It's here. IB1 flows over here. It's here, IB1. After this, it becomes IE. After entering into this emitter, that becomes IE1. And yeah, we are done with this one. Here, we are done with this one. It's also done. So it is continuing. It is continuing like this up to that place. What? On the other hand, we have here, it's like this. And RC, we have RC like this. And connected to plus VCC, it's a DC that will be eliminated here. This is it's grounded, it's made 0. And what current flows over there? It's here, change in the color for you to understand. It's IC1 over here. We are done with this half part. This one, this is done. So this is there, it's here. So drawing that side, what it is, it's for you to be more clear, we have similar to symmetrical, it's symmetry, right? The same symmetry to be drawn over here. We have a base over here and provided with this one I'm drawing this one, this V in 2 and over here this one, and we cannot neglect this one, RI2 source resistance, internal resistance of the source, right? And what current flows over here? It's a IB2. IB2 will be flowing, this one IB2 will be flowing, and this has to be drawn, that comes at the end like this one. Now here it's RC and have to connect to VCC. It's a AC equivalent, DC is made 0 and grounded, so that's the reason. And what we have over here, it's a IC2 we have on that side, right? This will be the AC equivalent. Guys, I'm not yet done. We're talking about AC, AC voltage, AC currents, dynamic, those are changing. So a dynamic resistance appear across emitter over here. We cannot show over here, but that should be shown in the AC equivalent. So dynamic resistance RE, dynamic resistance RE. So where is the emitter? That has to be marked, that appears, and that has to be shown in the AC equivalent. Where is our emitter? Here it's our emitter, right? So here we have that dynamic resistance. While we talk about AC, that comes into the picture. We have RE over here, and same like even this one, even this emitter has that more clear, to be more clear, it's a RE over here, right? Make a note, it's the dynamic resistance. It's a changing voltage, changing current, so changing resistance, and that comes into the picture when we talk about the AC analysis, right? So going ahead, and guys, we should mention this IE1 and IE2. Here we have that after base we have IE1 over here, and we have IE2. Now yeah, it's perfect. Now this IE1 and IE2 flows in this direction, IE1 plus IE2, that goes, and here it's grounded. This is to be grounded, right? So this is one. And analysis, some writing down the equation, the voltage drops, this one for this loop, equation for this loop, right? And for this loop, what we have is this voltage drop is equal to this voltage drop plus this voltage drop plus this. So how to write down that? V in 1, it would be better if you go for black to be more clear. V in 1 is equal to this voltage drop will be equal to source, will be equal to this plus this plus this. So how to write that one? This one is IB1 RI1 plus this drop, it's a IE1 it's a RE plus this drop. What is that drop? RE into IE1 plus IE2. Hey guys, is that clear? Now guys, this IB, like we have IE1 and IE2, right? So let the entire equation be in terms of emitter currents, IEs. So what this IB is doing over here, let me change to IE. How can this be written here? RI1 as it is. Now go back to this one. Yeah, go back to this one. From that one, this gives us IB can be substituted with IE upon beta AC, right? So that plugging over that side. So it's a IB1, so it will be IE1 upon beta AC. We're talking about AC equivalent, right? So this is the case, plus IE1 RE plus IE1 RE plus IE2 RE, writing the drop for this loop, Thevenin's voltage drops for this loop. And guys, IE1 can be taken out as common from all this one. Yeah, we can. IE1 taking out as common, what we have is RI1 by beta AC. It's a suffix, okay, don't mind. It's a AC plus IE1 came out, it's a RE plus this RE plus IE2, guys, IE2 RE. So this is the expression for V in 1, right? V in 1. So we have that one. And guys, when compared to this one, the beta of any transistor will be very high. You can find out that in any numericals given. It will be in the order of hundreds, 200s, 150, etc. It will be very high, and this will be very low, and this fraction will be very low. This RE plus RE is very much larger than this one, then this can be neglected. Why? Because I am writing over here RE plus RE is very larger than RI1 by beta AC, right? So in that case, we neglect this one. This can be neglected. We can consider only this one. So new equation for V in 1 will be here. I guess you won't get confused if I write over here. V in 1 will be what is that? IE1 U1 into what is that? Will you get confused with that? RE plus RE, capital RE plus IE2 capital RE. Guys, don't get, I'll put it in a box, okay? Don't get confused. This is our expression for V in 1. A lot of analysis. This is important equation, right? Make a note, please. This one we have to obtain the expression for this one also. Writing the expressions for V2, this loop will help us to evaluate the expression for V into similar to this one. So what is that expression? This drop supply will be equal to this drop plus this drop plus this drop. So I have to write that one here. It's a V into V in 2 will be equal to, what is this drop? IB2 it's a RI2 plus it's a RI2, okay, IB2, and this drop, that's a IE2 RE, the dynamic resistance, plus IE1 plus IE2 into RE, capital RE, the external, this one RE, right? And we once again all the equation, the entire equation in terms of emitter currents. So this base current has got nothing to do over here. You're making use of this once again. That can be transformed to, which will be equal to like RI2 as it is. Now this one will be IE2 upon beta AC, right, from a transistor, that equation, plus going ahead IE2 RE plus IE1 RE plus IE2 RE. This will be the equation for IE2 RE, and this one for the second one. And IE1 over here, IE2 into this one, taking out IE2 as common from all the terms. What we have is RI2 by beta AC suffix, we are talking about AC, plus we have this RE, the dynamic resistance, plus capital RE, external emitter resistance, plus IE1 RE, this expression, right? And here this entire term, here what we have is once again the same discussion which we made use of that one. What it is, RE plus RE practically will be very higher than RI2 by beta, and so for the next expression we can neglect this one, which gives our, what it is, V in 2 will be equal to, here IE1 in an order, RE plus IE2, this IE2, neglecting this one because this comes into the picture, RE plus RE into RE plus RE, guys. So here this is the expression for V in 2. Now we have obtained the expressions for these two, we don't need this anymore. You cannot see this anymore. I need this place. Make a note, please. Now these equations, whatever I had written previously over here, I have rewritten over here without any mistake perfectly. I didn't miss any term, right? Going back to the circuit, what will be VC1? Here we have VC1, okay, we have VC1 over here. What will be VC1? We need that one. VC1 will be equal to RC IC1, and what about VC2? We have same RC IC2, okay. Please keep that in mind. Even this needs, we will be in need of this one. And here equation 1 and equation 2 on this side, this can be put it in a matrix form. How to write that in a matrix form? Here we have V in 1, V in 2 over here, it's like this, which is equal to something like here into IE1 IE2. This is how we put it, this entire equation in matrix form. What we have, RE plus RE over here, and this comes over here RE, and on the other hand this comes over here RE, and this comes over here RE plus RE. Alright, now evaluating for E1 and E2, making use of Cramer's rule will help us to reach that derivation which we are in search of. So how to evaluate for E1 using Cramer's rule? This is the procedure. E1 will be given as here IE1. Don't shout at me. It's a IE1. IE1 will be equal to what? The determinants. It's a first one. So plugging in this one over here, here, changing the color, V in 1, V in 2, and RE and RE plus RE and its determinant, okay, and the whole, the determinant of this one. So how is that written? RE plus RE, and we have RE over here, it's RE again, RE into, it's not into, this element RE plus RE, making no mistake. Now the determinant of this one, this obtaining, now this ratio will give our IE. So how to obtain the determinant? IE1 will be equal to, hey guys, this fraction as it is here, it's as it is, this into this minus this into this, right? V in 1 into this one, RE plus RE minus this into this, in the sense V in 2 Re, external resistance, right? And in the same way, it's in the denominator, it's a Re plus Re whole square minus Re square. This into this minus this into this, so that will be that one, right? So this is for IE1. Now guys, you evaluate them following the same procedure, right? Here itself, plugging in V in over here and follow the same procedure, you'll be having IE2 will be equal to, trust me, this is going to be that V in 2 Re plus Re in minus V in 1 Re, and it will be the denominator as it is, Re plus Re, this Re whole square plus minus Re square, very sorry. So this will be the expression for IE2. Please, you check it. From the first circuit diagram, we had V0 is equal to RC into IC1 minus IC2. RC as it is, in a transistor, IC1 will be equal to, IC will be approximately equal to IE. So this could be plugged with, this can be plugged in this value. And IE1 we have evaluated making use of the Cramer's method. That matrix and Cramer's method, this is the equations I have rewritten. IE1 is this minus RC as it is, IE1 minus IE2 is this. Okay, so solving for this one, what we have is V0 will be equal to RC, making no mistake, RC is as it is, and in the denominator what we have is, it's common, right? It's a square, sorry, it's a square, Re plus Re whole square minus Re square in the denominator, and cross multiplying it will be V in 1 into Re plus Re minus V in 2 Re minus that one, V in 2 minus V in 2 into Re plus Re minus V in, sorry, it's plus V in 1 Re. Hope it's going correctly. Yep, it is. Is that clear? So cross multiplying this one, we have this one. So V0, further V0 will be equal to RC as it is. Hey guys, it's a plus B whole square. So that will be Re square plus twice of Re into Re plus Re square minus Re square, and in the denominator, you guys are taking Re, this one as common from this and this. So here changing the ink so that it will be easy for you. Re and Re as common from here. So what we have is Re plus Re as common from that term. So we'll be left with V in 1 and minus V in 2. Okay, and going ahead, plus. So what if we take Re as common from here and here? Yeah, we can take, and what we have is Re into, so we are left with V in 1 minus V in 2. I hope it's clear. And here going ahead, that side, don't miss the focus. Okay, so here Re plus Re square minus Re square gets cancelled. So moving ahead, it will be RC as it is, no change in the RC. RC will be equal to RC upon, guys, this can be a small modification over here, please make a note. Re into, Re came out, so it's Re plus Re came out, so it's twice of external resistance, emitter resistance, Re. And on the other hand, V in 1 minus V in 2 as common from here, that's V in 1 minus V in 2 as common from here and here. So we'll be left with Re plus this Re. here it's RE plus this RE plus this RE, that will be twice of RE. So twice of RE. By now you should be at the end, you may be able to make out what happens next. So here RE plus twice of RE, RE plus twice of RE gets cancelled. So V0 will be equal to RC by RE, the dynamic resistance. And guys, it's a V in 1 minus V in 2, the difference input voltage. So that can be written as VID, okay, from which we have V0 by, it's a input voltage, difference input voltage, V in 1 minus V in 2. This is the ratio which is equal to RC by the load resistance, collector resistance RC by the dynamic resistance RE. This is output voltage by input voltage, and it's a voltage gain expression for the voltage gain of what? This one, dual input balanced output configuration of a IC741. Please make a note. Hope you understand. Hope you are able to catch the derivation. Support me with your valuable subscription and a share. Thank you so much.